Introduction. The aim of this experiment was to show the Torricelli theorem through comparison of theoretical velocity and experimental velocity of fluid. This experiment was conducted by use of cylinder tank with drill hole. The different height of drill hole from the ground surface are used for the experiment, which are 0.701 meter, 0.5 meter, and 0.29 meter. Objective of this experiment first is to understand Torricelli's relationship by comparing measure and theoretical value of velocity. Second, to learn the relationship between Bernoulli equation and Torricelli law. And the last one is to explain the dependent, independent, and constant variable. In theory, for Torricelli theorem, we assume the fluid flow is an ideal fluid and apply Bernoulli equation between 2 points. Equation 1 is Bernoulli equation where P is pressure, V for velocity, Z for height, and G is gravitational acceleration. From equation 1, we assume Z2 equal to 0, Z1 equal to the height of the water exit from the free surface. Meanwhile, P1, P2 is equal to 0 since the fluid's flow is open to atmosphere. Next, we also assume V1 equal to 0 since the fluid flow in a large size tank. After rearrange the equation, we obtain the velocity for theoretical and measured equation.
Hi, my name is Ahmad Zakar bin Anwar and I will continue with the methodology of this experiment. First, the apparatus was set up based on 3 different stages which are 0.7, 0.5 and 0.3 meters. Next, the height was measured from the floor to the orifice. Next, the water was filled into the cylindrical tank. We started with a volume of 1.5 liter of water. The hole at the cylindrical tank was covered with a thumb when filling the water. After that, take off the finger from the hole and the maximum distance was marked using a clay and time was recorded. Lastly, the procedure was repeated by using the different volume of water and at different height of stages.
So, good day, my name is Pei En from group 7. So, I'm going to explain about our table result and calculation. So, this is our table result for this experiment. So, in this experiment, we took 3 different heights, which is y equal to 0.70104 meter, and the second height is 0.50038 meter, and the third height is 0.29972 meter, which is the height measured from the floor up to the orifice. So, as a short form, we just give it a variable as y. So, continue to calculation. So, first we have to calculate the average initial water level, which is h, because we repeat the experiment twice. So we have to divide both of the data to 2 to make sure our calculation is accurate. So secondly, calculate the average maximum water trajectory distance x average. Same as above, add both of the data taken in experiment and divide it by 2. So third, also calculate the average time taken for water to drain out. Same as previously, add both of the time and divide it by 2. And 4, calculate the water flow rate by using the volume and divide it by T average that we calculate at step 3. So next, we have to calculate the theoretical velocity of water, V theo, by square root 2 times gravity and also the h average calculated as previously. So by using this formula, we can get the theoretical value for our water velocity. So finally, we have to calculate the experimental velocity of water. By using this equation, x average that we calculated previously times the square root that g divided 2 times y. So in this case, we can get the experimental velocity of water.
Assalamualaikum and hi doctor. My name is SETK2721-FLUIDS and now I will present our discussion part. So, firstly, we make selections on dependent, independent and constant variable. In this experiment, the dependent variable is the experimental velocity of water out from the orifice, or we call it as V measured in unit meter per second. So the formula need to be considered is the V measured formula. For independent variables are the height of initial water level to the orifice, H, and the height of orifice from the ground, Y, in meters respectively. In this case, 1.5 liter of water was initially filled in the cylinder and the water level H calculated is 0.9881 meter, and then the height of the orifice from the ground is also will be considered with three different heights, which are 0.3 meter, 0.5 meter and 0.7 meter. And next, the constant variables are the type of the fluid used, which is water, the pressure of water also constant, and the diameter of the orifice D also fixed, which is 1 cm to 1 cm. Next, how to relate Bernoulli equation with Torricelli's law. In this case, a few assumptions were made to the overall system and its calculation to achieve the relationship. The fluid flow in the streamline was first assumed as having a steady flow, being incompressible, and friction between the air and the water was negligible. Next, it started with the derivations from Bernoulli equation. Bernoulli equation stated that V is the velocity of the fluid, G is the acceleration gravity, which is 9.81 meter per second, H is the height of fluid from the reference point, P is the pressure, rho is the density of the fluid. Then when Bernoulli equation at 2 points, pressure at point 1 P1 and pressure at point 2 P2 was considered as constant at atmospheric pressure, which is equal to 0 and can be cancelled out. Velocity at point 1 V1 was assumed to be near 0 and can be neglected, and H2 was assumed as 0 since point 2 was set as the datum, which is a reference point. After combination of all parameters, the new derived Bernoulli equation was shown, which is H1 is equal to V2 squared over 2G. After rearranging an equation, equations of velocity which obey Torricelli's law was shown, which is V2 is equal to 2GH1. After that, we do the calculations on percentage of relative error for the theoretical and measured value. The percentage of relative error can be calculated by using the formula percentage error is equal to V theoretical minus V measured over V theoretical multiplied by 100. So the theoretical velocity of flowing fluid depends on the gravity constants and the height difference between the orifice and the surface of the water. The formula is V theoretical is equal to 2GH. The measured velocity of V measured when the fluid leaves the orifice can be obtained by considering the maximum horizontal distance traveled, which is at. The formula is V measured is equal to at G over 2y. When we compare the theoretical velocity and the experimental velocity at height from the floor to the orifice for these three heights, we can say that the percentage error that has been calculated for y is equal to 0.3 meter and 0.5 meter, most of it is more than 10%. It is due to maybe some error when doing the experiment. While for y equal to 0.7 meter, the percentage error is less than 10%, which can be acceptable for the experiment. Next, as we can see from the graph, All the graphs shows the theoretical velocity and measured velocity measured by the apparatus against the height of water level in the cylindrical tank. Based on the three graphs, a trend can be discovered for the theoretical velocity and experimental velocity measured, which are: when the water level in the cylindrical tank increases, the velocity of the exit fluid increases as well. This is because the hydrostatic pressure will increase consequently with the distance of the orifice from the water surface, which is that of the cylinder, and this condition obeys the Torricelli'S theorem. In this experiment, there are several sources of errors. First, position of the cylindrical tank may not be in an upright position, causing the maximum horizontal fluid travel to be inaccurate. Second, minor cracks in the cylinder and orifice will cause water to leak out, reducing the maximum distance traveled by the water. And third, premature or delay reactions when starting and stopping the stopwatch will affect the calculations. So, to minimize the first error, the position of the cylindrical tank should be maintained and fixed in an upright position. To minimize the second error, condition of the apparatus has to be checked and make sure it does not have any minor cracks in the cylinder. And to minimize the third error, observer eyes should always be perpendicular to the readings of the water stream distance to avoid parallax error.